Hi, so we're going to go over the product and quotient rule. But before we do, I'm just going to label P rule at the top. This is the proof, so I'm just going to label that just so you know that we're doing the product rule. In fact, if you want to skip to a different part of the video to see a different proof, then you can go and do so. But I'm just going to explain it. So let's start with the function, and it's going to be the entire function of f of x times g of x. All that means is it's two functions multiplied together, much like x squared sine x. But I'm not going to do any actual application today. We're just going to go over the proofs. So that means the derivative of f of x is easily just f of x plus h times g of x plus h minus f of x g of x. So just the slope formula again, as h approaches 0, but I'm not going to write that. We just add the term f of x plus h times g of x in the numerator. And I guess you could do this whatever way you want. But again, when you add and subtract something, you just you're not changing anything because you're just adding and subtracting. So it's going to be plus x plus h g of x minus this term again. And again, if you subtract and add, you can just cut these out. Again, same thing. So now we get, and we're going to factor out f of x plus h on the top. So it's going to be g of x plus h. And where else can we factor out an f of x plus h? Well, we can factor out an x plus h right here. So we get minus g of x. And remember, this entire thing is all over h, so we could just apply the h here. Or you could apply the h here, but it doesn't really matter. I just apply the h here because it looks more pleasing on the eyes, and then that gets the derivative definition in a little bit. And here on the top, we can just factor out the g of x. We can factor the g of x here. And again, that's a positive term, so it's f of x plus h minus the f of x we're factoring out here over h. And look, these are just derivative definitions. So we get f of x plus h times the derivative definition, so times g of x, plus, again, the same thing, g of x times the derivative definition, so it would just be that derivative of f. But we note that h is going to 0, and again, as h goes to 0, this is becoming f of x. So it's just going to be f of x, g of x, plus g of x, f of x. So that is your product rule right there. Now we get to the quotient rule, and this is a little bit more difficult, so bear with me here. I'm going to have to assume you know a little bit of algebra, and we're going to put this, hold on. Looks like the G rule. We're going to put this top left. So it might be a little bit harder to see, but we'll let the elementary function again be f over g, and this time I'm not going to write f of x because it's kind of tiresome. So if we start with the derivative, then the derivative of f of x is just going to be equal to f of x plus h over g of x plus h minus f of x over g of x over h. So yeah, that's all it is. Now what we're going to do is times g of x plus h on the bottom and the top. So it's going to be g of x plus h times g of x times h. And again, if you know your simple algebra, you just apply that to both numerator terms here. And the g of x plus h just cancel out. And you get f of x plus h times g of x minus f of x g of x plus h over this entire term here. And if you want to prove that, you can actually just hold on. You can actually just cancel the things out and see how it works out for you. So now we're going to subtract and add f of x times g of x to the numerator and denominator. So let me move this all the way to the top, like that. Great. So now we're just going to add f of x. I'm going to try to write this smaller and smaller. But yeah. G of x plus h plus f. I guess I could do f g of x minus f g of x. And again, this is just f of x times g of x and f of x times g of x. But I'm too lazy to write the f of x. So yeah. Now what you're going to do is you're going to apply the h to the top. So all that means is we're just going to apply this numerator and write it in a different format. And we'll get something like g of x minus f of x. Actually, yeah. So this entire thing right here, actually I could just probably do this. Make it a lot simpler. over h over h over h over h, which is the same exact thing because you're just dividing each term, and then over this entire thing, except now the h is distributed to each part or each term. Now let's move this upwards again, because it's a pretty not. This is actually a simple proof, but I don't know why it's taking a lot of my space. So we're just gonna move it up again, and we're gonna keep it in view just so we know what the next step is. And now what we're gonna do is we're just gonna rewrite the function, and it's gonna be. I'm not gonna write the limit. Actually, yeah, maybe it is better to write the limit. So limit as h of o, and we're just gonna factor out a g of x from the f of x plus h. So again, we can factor out a g of x here. So it's f of x. Oh, sorry, f of x plus h minus the g of x we factor out from here. Actually, it would probably be right here. Minus f of x over h, and we could just, they're like terms, so we could just do that. Minus, and then we're going to factor out an f of x from the top. When we can factor f of x here, so that's going to be g, actually that's a negative term. Wait, yes. Hold on. Oh yeah, because we're applying the negatives. And since we're already applying a negative here, because this term makes a negative, we just do f of x plus h. And since we're factoring out a negative, we also have to factor out one here. So it's going to be minus f of x plus h minus the g of x we're factoring out there. And if you want to see the proof, oh sorry, let me just hold on, I'm trying to, oh wow, okay. So I'm just gonna write it a little bit smaller because I don't have that much room. So limit as h approaches 0. And now we're gonna factor out an f of x here. And again, since this is a minus here, or you could just do plus just for sakes, but I'm not gonna do so. It's gonna be minus, so we're factoring out a minus f of x here. And since we're factoring out minus f of x here, it's just gonna be g of x plus h. And then we're factoring out a negative f of x here, which is just going to be minus g of x over h. Again, what does this look like? This looks like g of x times the derivative of f of x minus f of x times the derivative of g of x. And it would be the limit as h approaches 0 of the numerator, which is just g of x plus h times g of x. What happens as h approaches 0? Again, same thing. It's going to be g of x times the derivative of f of x minus g prime of x. Or actually, to keep it homogeneous, I'm just going to put the derivative as the second part, or the second product, minus f of x times g prime of x all over, and this is approaching g of x, so it's just going to be g of x squared. And that is your proofs here. Really beautiful. Whoever figured this out was a genius. I'm sure they figured this out back in like the 1700s. So yeah, that's the proof.